Hello and welcome to Unit 4, Probability Distributions. This is our final unit of study for the data management course. So probability distributions is the topic, or is the unit name, and it's also the topic today, probability distributions. So what's your goal for today? Once you've completed the note and gone through the homework, I can explain and apply my understanding to probability distributions. So we're just looking at being able to describe, explain, and work a little bit with them. So in previous units, the emphasis was on determining the probability for one event to occur. So how many ways can you have 2 boys on the committee? How many ways can you have 3 wins in a best of 5? This one is significantly different because we're no longer looking at one outcome. We're looking at an analysis of all outcomes. So we are looking at the probability distribution, the probability of all events occurring. So we're not focusing on just one event. We're looking at all events to occur. So some of the terminology, and you're going to be saying, I've already seen this is in my note, and that's good that you recognize it. We need to look at it one more time because there are 2 distinct types of probability distributions. There's discrete probability distributions and continuous. So our discrete probability distributions, a discrete one has values that are separate from each other and or must be integer values. So your example of this would be people, wins, tickets, something you cannot have part of. However, with continuous variable, and we're going to get into that later in this particular lesson, this unit, infinite number of possible outcomes. So if we're looking at time, you can have a part of a time. Heights, probability distribution of height, since there is an incremental amount of each. And we would have different heights. So again, very important that discrete and continuous continually comes up for us in this course. Notation. So the probability notation for distribution is quite different. So before, I'll just do a quick recall here. This was the notation we were using. P of x equals n of x over n of s. P was our probability. X was our value of interest. So that was for a straight probability calculation. When we deal with distributions, we now move into a little bit different notation, and then the notation looks like this. So it's still capital P for probability, capital X equals little x equals whatever equation. So we don't have 2 equal signs in this equation. Okay, it's still just one. It's an expression in here. So our P still stands for probability. Probability. The X, the capital X, is what we call our random variable. Our random variable. And what you're going to find is just a notation change, really. There's nothing, there's no difference in the calculations and so on and so forth. And then small x is still our value of interest. All right. So the only change is notation. That's the only difference that we're looking at here. So I'll just put that there. It's a notation change. And when you see this notation, you know that you are dealing with a distribution, which means we're interested in all possible outcomes. So the other flip side to this, and this is something that we had not discussed at length because it really doesn't work out when you're looking at a particular value. We're looking at expected value. So expected value is the quantity we would expect to obtain when the experiment is performed. So we're looking at, if we flip a coin, how many heads should we get, okay, and so on and so forth. So this deals with all cases. So when you're dealing with the formula for expected notation, the expected formula notation for the first types of distributions is a capital E, and it's followed by X, our random variable. So it's a capital X. And how you calculate it is that you take the value of each particular variable in question and multiply it by the probability of it occurring. So the formula is going to look a little strange here, and I'll explain it, and once you see it, you'll realize it just looks different. It's not really that complicated. Okay, so that continues for all the probabilities. It's like seeing the theoretical end of it until you see. I'm in the way that I need to see an application of it for it to make sense, the formula. Once I see that, then the formula does make sense. So moving along, uniform versus non-uniform distributions. So there are two types of distributions we're looking at today in the examples. The first one's a uniform distribution. A uniform distribution has each random variable has the same probability of occurring. So, for example, flipping ahead. Rolling a number on a die. Etc. All right, and when you get into uniform distribution, the formula for that distribution looks like this. So the probability of a random variable occurring is going to equal 1 over n. So there is a formula that will need to make its way onto your formula sheet. Because for a quick example, if we're talking about flipping ahead, so the probability of x equal to a head, it's the exact same as a tail. It's going to be 1/2, and so it's a uniform probability. All probabilities of all outcomes are the same. Non-uniform distribution is when the probability changes from experiment or outcome to outcome. So for example, we could be looking at the sum of 2 dice. Okay, we know that there's not an equal number of outcomes for that. 2 boys on the committee. Etc. So now you're looking at events that do not have equal outcomes when you perform an experiment. So the formula for that is as calculated, and I'll put that in. So the formula is as calculated in previous units. And like I said, I have an example that will bring this all together for us. Okay, so we are looking at 2 situations today. We are looking at a norm or uniform distribution where all probabilities are the same, and then we're looking at a situation where the probability is not the same each time. So there's a different probability on each iteration. Okay? All right. So moving on here. Just going to quickly go through this example. So determine the probability of distribution for a coin, tossing a coin 3 times. So going back to basically unit 1, and we're going to look at the 3 outcomes here, the 3 questions. We want a tree diagram, tabular form, and graph. So tree diagram, that's from our unit 1. Tabular form is now unit 4 for us, and the graph is the one we just finished, unit 3. So quickly, go through this. So tree diagram, so taking us way back. So 3 times, so trial 1, 2, and 3. So on the first one, you can get either a head or a tail. Head or a tail. Head, tail, head, tail. Down below, head, tail, head, tail, head, tail. So there's our tree diagram for that. All right. Now, tabular form, B part. Tabular form is basically setting up a T-chart for us, and I'm going to do it in terms of, I guess we'll do it in terms of heads here. We've got to pick one particular one. Okay. And we want to then, actually put that in the wrong column, I apologize. So this is going to be our small value x, and over here will be our random variable. So it's looking at how many heads we can have. So over here in the x column, we can have no heads, 1 head, 2 heads, or 3 heads, because there's only three layers here. So the possibility is 1, 0, 1, 2, or 3. What's the probability of each occurring? So it's just a matter of following the pathway. So for the first one, if I wanted to look at the possible ways to get no heads, that means it would be 3 tails. So there is 1/8 of a chance of that occurring. What happens if I want 1 head? So for 1 head, it would be tail, tail, head. So there's 1/8. Or it could be tail, head, tail. So that's 1/8. Or I could have did it head first, tail, head, tail, tail. So there's 1/8. So over here, there's 3/8 of a chance to get 1 head. How many ways can I get 2 heads? So tail, head, head. So that's 1/8. Head, tail, head. That's 1/8. Head, head, tail. That's 1/8. So that would be 3/8. And finally, how many ways can you get all 3 heads? That would be 1/8. So it's the exact same as what we did in Unit 1. The difference is, in Unit 1, we were only interested in how many ways to get 1 head, or how many ways to get 2 heads. Now, we have to show all possible outcomes, and that's what this tabular form is. We're looking for all possible outcomes, and I will add on to this note here, okay, this is a non-uniform distribution, because not all probabilities are the same. 1/8, 3/8, 3/8, 1/8. So not all probabilities are the same. If they were the same, it would be a uniform distribution. Final part's the graph. So C part, just want to insert a quick graph for ourselves here. And on the x-axis, we'll put heads. And we will go 0, 1, 2, and a 3. And on the y-axis would be probability. And I'll leave it in fractions. You can convert to decimals. So I'm going to go by 8ths, 1/8, 2/8, 3/8. That's as high as I have to go. And I'm going to use a bar graph here. So for 0, it would go up to 1/8. Then it would go up to 3/8, 3/8, and 1/8. So there is my distribution. And I just want you to note at this point the general shape of this distribution. Okay, not very important. The red dotted line is not something that's you need to worry about at this point. But so there's a distribution of a non-uniform. So it's just taking your tabular form and creating a graph from it. All right, we'll finish this up in the next segment.